Hello physics students, Mr. Dillick here, and welcome to physics videos number 20 and 21. I've combined these together. They are about Newton's second and third laws of motion, and it's about time we got to these. We talked about Newton's first law, so let's finish the idea. So first of all, let's remember, when we talked about Newton's first law of motion, there was a little bit of a history lesson involved there. Pretty much we said that we're in a branch of physics called dynamics, where we're trying to describe why things move, and that folks have been trying to do that for at least a couple thousand years, starting with Aristotle and his philosophical laws of motion. But the first scientific laws of motion were actually written by Galileo, who had two laws, and those laws basically described things that aren't moving and things that are moving. So he had a law of static inertia and a law of kinetic inertia. And the law of static inertia said that an object that isn't moving will stay not moving. It will remain unmoved unless acted on by an outside force. And the same thing with an object that is already moving. That's in kinetic inertia. If it's moving at a constant velocity, that is, if it's moving in a straight line, it won't, not changing direction, not speeding up, not slowing down, then it has kinetic inertia, and that's because it has forces that are balanced. Newton basically added that those situations will remain unchanged unless the forces are unbalanced, unless the equilibrium is broken. And that means you've got to have a force that's winning. You have to have, in a tug of war, a force that's winning the battle. And that leads us to Newton's second law of motion. Now, really what you need to know is that Newton's second law of motion says the same thing that Newton's first law of motion says, but it says it with math instead of with words. That being said, even though it says the same thing, its application is different. We apply it to different situations than we do Newton's first law. So let's talk about that. Newton's first law, we said, is the law of inertia, and I already described static and kinetic inertia to you. Newton's second law is that same explanation given in terms of math. That is, Newton says that a mass that is at rest will have a tendency to not accelerate unless acted on by an outside force. So you see those three things? Mass, acceleration, and force are in that description. Let's try it for the kinetic part. An object, a mass that's moving, will have a tendency to keep moving at the same speed, right? Not speed up, not slow down, not change direction. That sounds like not accelerating unless acted on by an outside force. So it is pretty much Newton's second law and the famous equation F equals ma that says in math terms what Newton's first law says in words. The application of Newton's second law is quite different, though, because we know that if you add up all the forces acting on an object and it's in equilibrium, that those forces will be balanced, that they'll add up to zero. F equals ma will add up to zero. That's a weird way of saying that, because F equals ma is a multiplication. We're saying the mass times the acceleration will equal zero. And also, if you add up the individual forces, they equal zero. So what we're saying here is that the net force is zero because either the mass or the acceleration is zero. One of those two things has to be true in order for the force to be zero. And we know it's not that the mass is zero, because then it would be massless and it wouldn't be an object. Since it is an object and it has mass, its net force must be zero because its net acceleration is zero, which means it's either not moving or it's moving at a constant velocity, basically what Newton's first law says. Okay, so F equals ma is true for individual forces. For example, gravity. We know that the force of gravity is, like any other force, equal to the product of the mass times acceleration. It's just, what is the acceleration of things due to gravity? Well, that's little g, the acceleration of gravity, 9.81 meters per second squared. So if you want to calculate an object's weight, you take its mass times the acceleration of gravity. You take whatever its mass is, let's say it's 10 kilograms, you multiply it by the acceleration of gravity, that's 9.81 meters per second squared. Its weight, the force of gravity, is going to be roughly 98 newtons. And so F equals ma is true for specific individual forces. It's also true for directional net forces. For example, the net force in the x direction. All right, don't let all the math scare you here. let's imagine that we had an object on a surface, and let's say that object was experiencing a weight, a force of gravity of 20 newtons and a normal force of 20 newtons. It was experiencing a applied force to the right of, which I'm going to call force 1, of 10 newtons, positive 10 newtons, and a force to the left of 4 newtons, which I'm going to call negative 4 newtons. Well, if we said, what is the sum of all the forces in the x direction, the directional net force, the net force in the x direction, will be the sum of force 1 plus force 2. So in this case, it'd be 10 to the right plus 4 to the left equals 6 newtons to the right. That means this force is 6 newtons bigger than that force in that direction. And then we can see that the net force up and down is 0 because gravity is 20 and downward, and the normal force is 20 upwards, so no net force there. So we might ask, what is the net force in the x direction by doing F equals ma? Well, what we would need to do is take our mass times our acceleration. And we know that that has to equal 6 because we just added it up. So we know that the mass times the acceleration has to equal 6. Well, I can tell from the force of gravity, which I know from right up here from the individual forces is mass times acceleration of gravity, that that's got to be basically negative 20 because it's 20 down, and that the acceleration of gravity is negative 9.81. I'm just going to round that to negative 10 to make it easy. The mass is about 2 kilograms. So if the mass is 2 kilograms and the net force in the x direction is 6 to the right, then that means our net acceleration in the x direction is 3 meters per second squared. And you could probably guess that our net acceleration in the y direction is going to be 0 meters per second squared because this doesn't appear to be levitating off the table or collapsing through the table. Okay? This is also true for total net force. If we go back to the previous example and we say, what is the total net force here going to be? It's going to be the sum of the force in the x direction plus the sum of the force in the y direction, which in this case is easy. Since there is no net force in the y direction, then the total net force in this case is going to be 6 newtons to the right, which means the total net acceleration is going to be 3 meters per second to the right. But what if we took the same example and we just tweaked it a little bit so that the net force in the y direction wasn't 0? Let's give it a try. Okay, again, so don't get too scared away here by the math. Basically, this is the same picture that we just looked at on the previous page, except I've added a third force, a 5 Newton applied force upward. So, and now when I ask you, what is the net force in the x direction, the directional net force? I've got plus 10 plus minus 4 is plus 6. So we have, between these two forces, this one is winning by 6 newtons to the right. And when we do the y net force, we now have 3 forces, a 20 Newton force down, a 20 Newton force up, and a 5 Newton force up. Well, these two cancel, leaving us with a 5 Newton force up. So when I go to find my total net force, these two are directional net forces. When I go to find my total net force, these equilibrium statements have helped me figure out that I need to draw this bow tie triangle, this right triangle, that shows us a 6 Newton force to the right, that's our total net force in the x direction. A 5 Newton force up, that's our total net force, or excuse me, I'm using the word total. Let me backtrack. Our 6 Newton force to the right, that's our directional net force in the x-axis. Our 5 Newton force is up, that's the total sum you get when you do the directional net force in the y direction. So to find the hypotenuse, which is our net force, and the angle, we need to use Pythag and inverse tangent. So we can see that the total net force is going to be the square root of 6 squared plus 5 squared, and we can see our inverse tangent is going to be the inverse tangent. Our angle is going to be the inverse tangent of 5 over 6. And that's how you'd find the total net force. Awesome. Okay, so now on to video 21. So remember, what we just said is that Newton's first law of motion is the law of inertia. We've been over what it says. It has 2 parts, static inertia and kinetic inertia, that describe things that aren't moving and things that are moving. And Newton's second law describes it in math. So what does Newton's third law state? Something similar? Well, not really. It actually says something quite different, but it definitely relates to both Newton's first law and Newton's second law. Newton's first law basically is what you use when forces are balanced. Newton's second law is basically what you use when things are unbalanced. And Newton's third law is kind of none of the above. Newton's third law can only be used in a very, very, very specific situation, only in the case of static equilibrium is it entirely true. In the case of kinetic equilibrium, it is sometimes true. And in the case of non-equilibrium, it's never true. So Newton's third law is sometimes called the vector law because it describes forces as vectors having magnitude and direction. The actual law says for every action there is a reaction that is equal in magnitude and opposite in direction. Well, we're talking about magnitude and direction, so that means we're talking about vectors. So you can see why sometimes people call it the vector law. But more often than that, it's called the action-reaction law because, again, it says for every action there's an equal and opposite reaction. So it's talking about forces coming in pairs called action-reaction pairs. And you're going to get some practice on some homework identifying those pairs. But pretty much what it's saying is, for instance, if you push on the wall, if you're wearing roller skates and you push on the wall will push back on you. And so, in the case of balanced forces, in static equilibrium, those forces will be equal and opposite. But if you push hard enough that the forces are unbalanced and something moves, then you're not in kinetic or static equilibrium anymore, then the forces still come in pairs, and they're still opposite in direction, but they're maybe probably not equal in magnitude because you got an acceleration. And so you can use Newton's second law to find out what that acceleration is. All right, this is where we get the idea of the normal force that we talked about before. This force exists only in static equilibrium as a force that is equal and opposite. Now, it still exists when you have non-static equilibrium, when things are unbalanced. It's just not equal and opposite. It's no longer true that when you touch something, it touches you back exactly hard as you touch it. It now touches you back, but less so. And that's a pretty important idea. Okay, so Newton's first law, inertia, Newton's second law, which is F equals ma, Newton's third law, which is the action-reaction law, work together to describe situations. So all along we've been doing free body diagrams to help us analyze the forces so we can decide which of those three laws, if any, apply to that situation. Sometimes only one will, sometimes they all will. It kind of depends on the situation.